Hello, welcome to Algebra 2, our first lesson on vocabulary and order of operations. I ask again that you take notes in an instructional manner like we did in class, and please follow along, pace yourself, and pause the video whenever it is needed. Let's begin our lesson, vocabulary and order of operations. All right, we're going to start off the year defining some of the things that we need to go over so that when I say the words in class, you know what it is that I'm referring to. So the first thing that we're going to look at are words that represent for us our number system. And what I'd like you to think about is I'd like you to refer back to when you first learned to count and think about how or what that number first was. And hopefully, when you think back, whether through babysitting or working with your younger siblings, you know that we naturally learn to count by starting with the number 1. From there, we go on to 2, 3, 4, and so on. So as we look at this particular number system, how we naturally start to count is by, again, numbers 1, 2, 3, 4, and so on. Notice here, as we look at these numbers, that there are no fractions, no decimals, no zero as we look at this particular set of numbers. So again, no zero, no decimals or fractions, and no negatives. When we look at our whole numbers from our list, what we're going to notice here is our whole numbers. We're now looking at everything that we learned or how we counted, but our natural progression in the world of kindergarten was that you learned when you had a toy, somebody took it away, that we ended up with nothing left. And we recognized that our nothing meant 0. So whole numbers start with 0, and then they follow all of the natural numbers. So notice that we still don't have any decimals or fractions and no negatives still at this point in time. Now from here you learned our number system, our placement system in terms of tens. You learned that we went up by 10s and 20s and 30s and so on as we looked at our number system. Also, add, subtract, you learn to do multiply, divide with whole numbers. Pretty much your whole elementary background worked with whole numbers. The time that you got to our 5th grade or 4th grade year in elementary school, you started to work with your division. Now, division is particularly known for us as rational numbers, but I'm going to change this up a little bit and define first our integers just because of our natural progression. So when you look at integers, notice that when we have our natural numbers, the 3 pieces we didn't have were 0, decimals or fractions, or negatives. Whole numbers added 0, but we still didn't have no decimals or fractions and no negatives. So now we're looking at specifically integers and saying of the 2 pieces that we don't have left, no decimals and fractions and no negatives, integers for us, which is one of the critical pieces or terms that you need to know in the world of algebra, actually pick up our negatives but still leave off our decimals or fractions. So our negative numbers, remember, work in the opposite of our positive values. We progressively, as we work left or right, get to larger values, but it's almost like a mirror image on either side of 0. Symmetrically, they open up in the same manner, just opposite signs. So our integers have 0, have our natural numbers, have negatives, but they still don't have decimals or fractions. So as we build off from that, and now we go on to rational numbers, you'll notice that rational numbers specifically, you would say, oh, well, there's my pickup of all of the other things, plus also decimals and fractions. And what I really want you to think about here is that rational numbers for us are defined to have specifically a repeating or finite value. So if you look at rational numbers, one might think 0 is a finite value, and you're correct, an ending value, something that terminates. So is 0.5, which can also be written as 1/2. Now the repeating part of it, as we look at these values, could be 1/3. We know that 1/3 is specifically 0.333 repeating. And that's what defines for us our rational numbers, repeating or finite, something that ends, values. Please note that rational numbers have every part of the natural numbers, whole numbers, and integers. Every part is embedded inside of those, but it also adds repeating values and fractions as well. Now, an irrational, notice that the word here is ir in front of the word rational. What that IR stands for us is specifically irregular. Irregular or different values that are not repeating and not finite, not terminating. And that's the definition of an irrational number. Never ending and never repeating. And as you look at that, the best value or symbol that we have to represent an irrational number that you're aware of now is pi. It's probably what you've seen from your geometry experience. If you're in geometry this year, most likely you saw it in your middle school experience. I'd also like to put down the square root of 2 because this year we're going to talk about radicals, which is what that is. And again, if you've had your geometry background, you've experienced radicals. Now the last definition for our number system is our real numbers. What we needed to have is if a group of words or two words that for us put all of this together to say that all of these numbers that are embedded in each of these things are important for our number system. So real numbers is everything you can graph on a number line or on a Cartesian plane. So as you look at what it is that we can graph -3 on a number line. We can graph 0 on a number line. I can estimate where 1/3 is on a number line. I can estimate where pi is, 3.14, and the decimal goes on and on and on a number line. So our real number system is saying, I'd like you to take all of these numbers and put them together. Some more definitions that we're going to go over here are geared up for us to try to allow us to understand what steps and procedure that we're going to do today with our world of order of operations. I'd like to start off first and define that the word expression, if you ever see it, specifically means that we do not have an equal sign shown. That's what the word expression means. That you will physically look at a problem, you might add in an equal sign, but there is none shown. Our numerical expression, which I'll just abbreviate here as EXP, as we look at a numerical expression, what we're saying here is values, so numbers that we have that we just learned about, operations such as add, subtract, multiply, divide, all of those will come to place, but there still will be no equal sign shown. So if I look at a numerical expression, it can be as simple as 2 plus 3. That's what a numerical expression is. Again, we might add in ourselves what the equal sign is, but it's not there initially. And a variable expression is something that builds off from the numerical piece of it. It has values, so it could have numbers. It has operations and also variables. And so an example that's a variable expression could be 2x minus 3 plus 5. Has a variable in there, has addition or subtraction signs in there, but we can't do as much unless we know what x is as we could with our numerical expression. Moving on, we have the word equation. An equation means that there is an equal sign shown. It means for us that we have two sides that are created, a left-hand side and a right-hand side. And typically on either side, you could have numerical expressions or variable expressions or both. And that equation tells us that we must solve for something. Whereas an expression implies that you need to do as much as you possibly can. The last part is the word evaluate, which is the set of directions you're going to work under today. The word evaluate means get one concrete value. Whatever it may be, get one specific answer. The last set of definitions that we have kind of all work together. You'll notice here that we have the word power, base, and exponent. I'd like you to connect the word power and exponent. They mean the same thing. It's just that sometimes when we talk about it formally, we'll say 2 to the third power is the verbal language, but ultimately the 3 in the power is our exponent. But they mean the same thing. Now our power and our exponent tells us how many bases to write. The key word is that you have to use multiplication. The base is the bottom number, and it's what is repeated. So if you look at 4 to the third, and we were to put it instead of exponential form, which is what you're seeing now, if we were to put it into what's known as factored form, stretched out form, you would say 4 is the base, so that's what I'm going to repeat. The power of the exponent, it says I'm going to see 3 4s, and I'm going to use multiplication in between. Now a common mistake for students is they'll say 4 times 3 is 12, so 4 to the third is 12. Now what I need you to remember is these specific differences. A 4 to the third means a 4 written 3 times using multiplication in between. It is critical that you remember what this means. It will carry throughout the whole year for us. So the next piece that I'd like to talk to you about